3.4, use inverse functions. The first step is always going to be to switch every x and y value to find the inverse function. Here is f of x, and this is going to be f inverse of x. You're going to switch every x and y value. So instead of having 0, 5, you're going to have 5, 0, 4, 1, 2, 3. And that is the inverse function. I can also do the same thing for ordered pairs. 5, 3, 4, 7, 8, 6. I would do the same thing on a graph. I'm going to switch every x and y value. The graph of the inverse is always a reflection of the original graph across the y equals x line. That 45-degree angle line, the y equals x. If I have the coordinate 2, 3, that means that 3, 2 will be in the inverse. 0, 3, 3, 0, and so on. What do we notice about these points? The function and the inverse. What we can see is that those points, we can switch the x and y values, but we're not always going to have a graph that has numbers on it. What we do know is that it's a reflection across the y equals x. It is perpendicular to the line. We can see that this is going on the diagonals 1, 2, 3.5 units away. And so this is going to be a half, 1, 2, 3 units away. The reflection is perpendicular to the y equals x line. Looking at the next example, we see that it's crossing the y equals x line. If I have 0, -1 in the function, that would mean -1, 0 would be in the inverse. And let's pick a point up here. This is about 1 3/4, 4. 1 3/4, 4. So I'm going to go to 4 and 1 3/4. Let's pick a point down on the end here. This is about -1.5, -4. -4, -1.5. And then what's going on around this area right here? I can see that the function is coming in and then going out. Let's pick a point that's out here, how far out that curve is going. And it's not quite at the corner of the box. It's a little bit more than halfway of the diagonal of the box. So I'm going to go in and go a little bit more. And that should be enough to sketch the graph. I see that it's coming in and going out. The function is coming in and going out. And then it's curving in, and it's curving in here, and then going back out again, away from the y equals x line. So we have f inverse of x, we have y equals x, and we have f of x. We can also find the inverse given an equation. In the first step, can you guess what the first step is going to be? We are going to switch x and y. So we have x equals 3y minus 5. Step 2 would be to solve for y. So we're going to shift the -5 over to the left by adding 5. And then divide by 3. The last step would be to substitute y inverse or f inverse of x for y or for f of x. Whichever one they gave you to start with, you're going to substitute it in. This says that y, the function y equals x plus 5 divided by 3. We just found the inverse, and so we need to notate that we found the inverse. Y inverse equals x plus 5 divided by 3. Step 2. Step 3. We can find the inverse with ordered pairs, a graph, or an equation. The inverse of a function f is also a function if and only if the horizontal line only intersects the function once. It's the same as the vertical line test. We like to do a horizontal line test to check to see if it's one-to-one. If a function is one-to-one, then we can find the inverse. If it's not one-to-one, then we can't find the inverse of that entire function. The vertical line test is to test whether it's a function, and the horizontal line test is to test to see if it's one-to-one. If I look at the quadratic here and do the horizontal line test, I can see that it is not one-to-one. Therefore, I would not be able to find the inverse of that entire function. If I look at the second example, I can see that no matter where I draw that line, that horizontal line, it's going to pass the horizontal line test. This would be one-to-one. Therefore, I could find the inverse of that function. Inverse functions, f and g are inverses of each other if and only if when I do the composition of f of g of x and I get the answer x, and when I do the composition of g of f of x and I get the answer x. Now this should make sense that I'm getting x for an answer when I do either composition. We just saw that when we had a function and we found the inverse, we were using the y equals x line as part of that technique. And so we are always going to get the answer y equals x, and if we don't, then they're not inverses of each other. It's important to understand that you need to do both of these compositions. You can't just do one. You must do both to check to see if they're inverses or to verify that they are inverses. We have f and f inverse of x, and we want to know, are these inverses of each other? We're going to start with the composition f of f inverse. That means I'm starting with my function f, putting a parenthesis for wherever I see a variable, and substituting in the inverse. I can see that when I do the distributive property, my 3 in the denominator is going to cancel, leaving x plus 5, and then I have the minus 5. And we get x for our final answer. Now we need to do the second composition, and that's going to be f inverse of f of x. So we start with the inverse function. And we're substituting in f into that variable x. And again, we're starting with the distributor property. 1/3 times 3x is x. 1/3 times negative 5 is negative 5/3. And I still have a plus 5/3. And we get x. Example 3 says, find the inverse of f of x equals x squared for when x is greater than 0. Let's plot x squared When x is 0, y is 0. When x is 1, y is 1. When x is -1, y is still 1. When x is 2, we get 4. The same for -2. And so here, this function x squared would not pass the horizontal line test. That is why we have a restriction here that says that we need to find the inverse for when x is greater than 0. So we're just looking here on this part, and that would make the function now 1-to-1 if I did the horizontal line test on just that piece. So sometimes they give us a condition, other times we have to make that condition ourselves. So we're going to find the inverse of this. That means I want to see my y equals x line. We're going to have 0, 0. And then we have when x is 1, y is 1. And if I switch those, that'll still be in the inverse. And we're going to take this point. 2, 4 becomes 4, 2. I can see f of x is coming under the y equals x and then crosses over. That would be true for the inverse. It's coming up over and then it's going out. So for this example, the only part we were actually looking for the inverse of would be this. That is what f of x is. And that is when x is greater than 0, making it 1-to-1. Consider the function and determine whether the inverse of f is a function and then find the inverse. All right, so we have -2, -1, 0, 1, and 2. -2 cubed is -8 times 2 is -16 plus 1. -1 cubed is -1 times 2 is -2 plus 1. 0 cubed is 0 times 2 is 0 plus 1. All right, so let's graph -1, -1, 0, 1, and 1, 3. This looks like a straight line, but you need to remember that a degree 3, how many turns does a degree 3 have, and in which direction are the tails facing? The tails are facing in opposite directions, and it has 2 turns. 1, 2 turns, and tails are in the opposite direction. So this is not a straight line. It's coming up, doesn't have very much of a turn, turning a little bit more again, and then going up. All right, so we can see that if we did the horizontal line test on this, it would pass. So we are going to graph the inverse and start by having our y equals x line. All right, we're looking for those points to help guide us in our inverse. We have 0, 1, so 1, 0 would be in the inverse. Where it's crossing right here would be in the inverse. We have 1, 3, so 3, 1. And we see that the function is coming in and then curving out. So the function is coming in and then it does curve out right here a little bit. And so just looking for that reflection piece coming out and crossing over. F inverse of x. All right, here we go. Finding the inverse. We start with that y equals x line. Looking for those guiding points. I see one here is a good one. And so we are diagonally one away again. That is the point 1, 3, so that is 3, 1. And we also have the origin. The function is going away from the y equals x line. The function is going away. How far away is it from the end of the axis? It's just over the 1 a little bit. So make sure I'm about right there. And there we have f inverse of x. This is 1 to 1, so I can find the inverse. Going to look for that 45-degree angle line. Looking for some good guiding points. For this one, it's just a little bit away. Make sure that I am perpendicular. This point that is out the furthest on that curve. Where it's crossing over. And then we'll pick a point on the end point. I see it's about this far away from the axis. This far away from the line. And another endpoint on the other end. You can have as many points as you need, as many guiding points. All right, and how far from the axis? About there. All right, so we know that it's coming in, goes out, it crosses, and goes out. And this would be f inverse of x. For the last example, notice that it is not 1 to 1. That means that I need to restrict the domain. So f inverse of x is going to be restricted. I'm going to do this piece this time instead of doing the same side that we keep doing. Let's do when it's less than 0. Less than or equal to 0. So I would like to find the inverse of this piece. All right, we have in f of x, we have 0, 1, so 1, 0. We also have, this would be a good point, that would be 1, 2, 1, 2, 3, 4, 5. 2, 5, that is negative 2. So down here, it did not look to be the same distance. And one last one out here, we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So negative 3, positive 9. We're going to go to 9 and then negative 3. We can see that the behavior is going away from the y equals x. We have f of x and we have f inverse of x. And this is for when x is less than or equal to 0.